So hi everybody. We're going to start with a quick review of what we talked about yesterday, which was the derivative of the natural log. So you don't need to take notes on this. This is exactly what we talked about yesterday. So we know that the definition of the natural log function is equal to the integral from 1 to x of 1 over t dt for x greater than 0, because of course the natural log is not defined when x is negative. And so we're going to take the derivative of both sides with respect to x, and we get that. And then we wonder what's happening on the right side. That part is cut off on the bottom. We don't know what the derivative of ln of x is, at least we didn't. But we do know how to take the derivative of the other side. And therefore we get the derivative of the natural log of x is 1 over x. Very exciting stuff. So we talked about the slope field already and what was going on there. And here is the definition. So go ahead and start taking notes here. We've got the derivative of the natural log of u with respect to x is 1 over u times u prime, with the derivative of the argument. This is basically just chain ruling. So we have u prime over u. So let's go ahead and use that in context. So we have find y prime if y is equal to the natural log of the tangent of x. So we know that if we were to apply this rule, we're going to use 1 over tangent x times the derivative of tangent x, which is secant squared of x. And so that is y prime. And that's the simple things. Now we're going to simplify this up a little bit. We know that secant is 1 over cosine, and tangent is sine over cosine. So 1 over tangent is cosine over sine, cosine of x over sine of x, times 1 over cosine of x squared, which is equal to 1 over sine x times cosine x. And there is our derivative, simplified up a little bit. So this is very simple simplifying. We know the cosine cancels out with one of those. That's where everything went. We could then move these back up just to have some more fun with it. We could say 1 over sine is cosecant of x, and 1 over cosine is secant of x. You could also write it that way. Any of these things would be fine. You can, of course, if this for some crazy reason was a free response question, you could have stopped here. We never know how far they're going to go. And so it's nice to just see some of the tricks we can play with sine, cosine, tangent to simplify. And that's just some of our opportunities. So let's go ahead and see what we have in store here. So some equations are ugly. So like this one, why would we want to take the derivative of this? It's really a very complex problem to take a derivative of. And so, but we've got power rule, product rule, quotient rule, chain rule, but we can play games with this and make it a really simpler problem. So let's go ahead and see what we can do to play some games with this formula. We can take the natural log of both sides. So by taking the natural log of both sides, we can actually expand this out to do different things. So we've got the natural log of y equals, this being expanded, would become the natural log of x, parentheses x minus 1 to the 3/2 power, minus the natural log of x plus 1 to the 1/2 power, we're going to use we're going to do a little bit more expanding on this side, natural log of y, and then we have the natural log of x plus the natural log of x minus 1 to the 3/2 power minus the natural log of x plus 1 to the 1/2 power. I'm going to use some power rules here. ln of x plus 3/2 ln of x minus 1 minus 1/2 ln x plus 1 equals the natural log of y. Now we're going to take the derivative of both sides. And so we have 1 over y, I really like this color pink I suddenly chose, times y prime, or dy dx. Let's go ahead and use dy dx there. We'll use y prime. Y prime equals 1 over x for natural log of x plus 3/2 times 1 over x plus 1, excuse me, minus 1, minus 1/2 times 1 over x plus 1, parenthesis right there. And so there's everything. We wanted to get y prime alone. So we're going to do that by, oops. So what we would have here, just cleaning this up a little bit. Okay, so you can see that I'm kind of out of room here. So we're going to just kind of move forward a little bit quickly. That's just the same stuff. Get ourselves some more room. So I'm just going to start over just a little bit and take this derivative of this implicitly. This is what I had a minute ago, but now I'm just going to give myself some room. So we have 1 over y times y prime equals 1 over x plus 3/2 times 1 over x minus 1 minus 1/2 times 1 over x plus 1. So this is my implicit differentiation, no big deal. I'm trying to get y prime alone. So y prime equals y times this mess. So 1 over x plus 3 over 2 parentheses x minus 1 plus 1 over 2 parentheses x plus 1. And there's my closed end of my parenthesis. And y, we knew from a minute ago, is that crazy equation we started with before we expanded everything out. And y goes in front of this and cleans it up. So we'll let the computer kind of handle this for me and see if we did it right. So let's see what happens. So there we are. Everything's there. Chain ruling there. And now we have that times y. Final answer comes right here. So that's everything where we were. And then we just stick the original equation right there. So that's where that came from. That's our original equation. And there's our answer. So all that work that we would have had to do just kind of gets handled by using natural log. It's pretty cool. Makes the problem much simpler. So what is the derivative of the ln of the absolute value of x? So x cannot be 0. And we already know by definition that u generally has to be positive. When we stick in the absolute value, we don't have that restriction. And so here's our rule. So it's basically the same, just that we can't have x here. So it's kind of weird. You just have some positives and negatives, so we'll see what happens as we get through some of the problems. So here we have y prime if y equals the natural log of sine of x. So y prime will be 1 over the sine of x, because it's just the u. So let's just go back and look at that really fast. So see how there's no absolute values on it? I was just double checking. So there we are. And times the derivative of sine of x, which is cosine of x. And so this equals cosine of x over sine of x. And y prime equals cotangent because cosine is on top. So that's what happened there. It's pretty kind of cool. And we know, of course, x cannot be 0. We still have that restriction. We can't have the denominator be 0. So we have to kind of look at that as this, in this case, the sine of x can't be 0. We already knew that because we can't divide by 0. So I have to keep those restrictions in mind. All right. Another problem. Find the relative extrema and inflection points. So this means we need to do possible points of inflection and relative extreme, maxes and mins. So that means we're going to take the first and second derivative of this problem. So the first derivative, y prime, is 1 minus 1 over x, which is equal to y prime equals 1 minus x to the negative 1. So y double prime is going to equal 0 minus negative 1 times x to the negative 2, or x to the negative 2, which is equal to 1 over x squared. So that's y double prime. So we've got our original y prime right there, and our second derivative. We need to set those both equal to 0. So 0 equals 1 minus 1 over x, or 1 over x equals 1, which means that happens when x is 1. 1 over 1 equals 1. So that's our critical point. Our possible points of inflection occur when 1 over x squared equals 0, which will never happen, but we have our, so that's never. But we also know when we divide by 0, that's another critical point, so x squared needs to equal 0. That's our other possible points of inflection. Possible points of inflection. And so that will happen when x is 0, so that's a possible point of inflection. We also know back here another possible critical point is x equals 0 because we can't divide by 0, so those are our critical points. And this is our possible point of inflection. And so we need to check our extrema. And we're going to do, we can use a first derivative test. 0 still doesn't work here. 1 over 1, so that's 1. It's positive, which means it's a max. Or we can do our sign line test. 0, 1, checking if the slope is increasing or decreasing. It's the same kinds of ideas. So when x is 0, and x is negative, natural log can't be negative, so we have a problem there. So x cannot be negative. X cannot be less than 0. X has to be greater than 0. And so, and x can't be 0 because we can't take the natural log of 0. So this is our only critical point. Now the question is whether it's a max or a min. So when x is between 1 and 0 or a fraction, we're going to get 1 minus a number bigger than 1, which is negative, because 1 over a fraction will be a positive, non-fractional number. And then positive 2, we're going to get 1 minus 1/2, which is positive, but small. And so it's always going to be 1 take away something smaller than 1. And so that's going to be positive all the time, making our slopes be negative to positive. So this is a min. And then our possible point of inflection. 0 is a critical number, but remember in our original point, 0 cannot be plugged into this problem, and therefore it cannot be a possible point of inflection, so there are none. And that's how we figure those kinds of things out. So that's your basic gist. I hope you do well. Good luck today.